any of you who aren't here can see it. We will just start with questions. I have there's going to be a couple people who are going to be taking the exam a little bit early, so because of that, I'm going to cancel tomorrow's office hour. I will be available via email, so if you have a question via email, you can certainly ask. But I don't want to hold an office hour if the exam is out there. We'll cancel tomorrow's office hour, but if you have last minute questions, please just reach out to me. Okay. So we will start. Anybody has any questions?
Synthesis number 6, please.
I'm sorry, I couldn't hear you.
I'm sorry, could we go over number 6 from problem set 9?
Can you type it in the chat? I'm not hearing you. I can hear you breaking up a little bit, but something number 6. Number 6, problem set 9. Okay, sure. Yeah, retrosynthesis problem. Okay, so let's draw this molecule out first. So we've got a ketone which has a tert-butyl group. Here we have a ether there. Okay, we want to make this molecule from right. From this one. Okay, so let's do a little bit of analysis of this system. Okay, everybody can hear me okay? Okay. So the first thing I would take a look at is what kind of functional groups do you have in your ultimate starting material, right? And in the ultimate starting material, you have an alpha beta unsaturated carbonyl. Right, and you've got an aldehyde. Right, so those functional groups are going to be important somehow to this molecule. Let's try to map out onto the product molecule where that starting material molecule is. All right, and so if we were to take this system, you'll notice that it's the 5-membered ring here, but then we got to decide how many carbons is that chain off of the starting material. It's 2 carbons long. So the 2 carbons that are part of that starting material are those 2 carbons. Okay, and so that's where the starting material is in the product. Okay. A couple other things we might notice, which is that the tert-butyl group has been added to the beta position of that alpha beta unsaturated ketone. So that's something that's important. Okay. Another thing that's important is we have a acetal functional group here. Right? Again, I know acetal is not on your exam, but it is a good review for the final exam. Okay. So we need to form that acetal somehow. So we can start to then piece things together. Maybe one more thing we can do is we'll notice that we've got this extra 1 carbon unit right here. Okay, got a 1 carbon unit that is hanging off of the alpha position to a carbonyl. Okay, it's a 1 carbon unit that has an oxygen attached. Okay, So how might we disconnect this, this molecule? Well, let's try to think about forming one of these functional groups in the last step of a synthesis. How might we do that? Well, let's think about making this acetal, right? Because the acetal is a functional group that you can make very easily by just taking an acid source, aldehyde or ketone, and an alcohol. So if we were to disconnect that acetal, let's say if we were to hydrolyze that acetal, what would we come up with? We would come up with a molecule that looks like this. Got a terp-butyl group here. The acetal hydrolysis would be that one and that alcohol. How would we form the acetal from that molecule? We would form it by using, let's say, HCl in methanol as solvent, because we have a methyl group as part of our acetal. Okay. So if you can see that that acetal forms from that aldehyde and that alcohol, you're well on your way to solving this problem. All right. So you want to try to do the functional group that's easiest to make in the last step of your synthesis. All right. And so we can go backwards from there. So let's try to do that. How could we go backwards from there? Well, we can use some enolate chemistry. Okay. We've got let me circle it here. We've got this unit right here. That is our starting material unit. And so the other two bonds that we need to break or make are this bond and this bond. And that second bond there is probably pretty easy to make, because that bond, right, is a bond that you can make via an aldol reaction, right? That's a beta hydroxy carbonyl. So what if we were to take this molecule and do a deprotonation, let's say sodium methoxide, followed by reaction with an aldehyde that would give us that substitution. What aldehyde would that be? It would be formaldehyde, right? Everybody agrees that that one carbon unit is going to be formaldehyde. Now, who sees a problem here? Who sees a problem with doing this reaction as drawn? What's the speed of an intermolecular reaction versus the speed of an intramolecular reaction? We've got another aldehyde functional group in here. So if we do the deprotonation with sodium methoxide, couldn't we just attack that aldehyde? We could, intramolecularly. And so it might not be able to compete with that acetal. Okay, fine. Let's remove the reactivity of that aldehyde. Let's make an acetal functional group or protection group first. Then what we can do is the enolate formation followed by trapping with your aldehyde, in this case formaldehyde, that gives you your alcohol. Okay, so I'm not showing this here, but what would happen is you would generate, let me just redraw this all out. That reaction would give you this, okay? And then you would need to treat that with HCl and water to give you the free aldehyde. Which then you would use with HCl and methanol to give you your ultimate product structure. Okay? Make sense? Okay. So we're here now. We've got this this protected acetal, protected aldehyde. How might we make a couple of the other bonds? Because we're actually pretty close right now. Pretty close to the ultimate starting material structure. Again, the strategy is to take a look at this and try to form the carbon-carbon bonds. The other carbon-carbon bond you need to make is that one with the tert-butyl group. And so we could make that by taking, let's say, an alpha-beta unsaturated carbonyl and reacting it with what? How would you make a carbon-carbon bond that does a conjugate addition, a Michael addition? What reagents would you use? How do you form a carbon-carbon bond at the beta position if your group that you want to add is a tert-butyl group? Right, so you want to do a 1,4 addition. The solution for a 1,4 addition of a carbon-based group is to use a cuprate. So we're going to use 2 tert-butyls, copper, lithium. Okay, that comes from taking tert-butyl lithium and adding copper iodide. Right, that's known as a cuprate. A cuprate is going to add 1,4. Work it up with a proton source and you get the 1,4 addition product. All right, we're almost home, right? How do we get to here from there? What do we think? How do you get from that ultimate starter material to the first step in your synthesis? What functional group are you making? Taking an aldehyde and making that functional group. How do you do that?
Would you use PTSOH and then a dialcohol?
Okay, so we need to protect that aldehyde as an acetal. And so in order to make an acetal, you take an acid source and a diol to give you the acetal, okay? All right, so again, we want to try to take these retrosyntheses and disconnect them into simpler pieces. This is a multi-step reaction. This is probably a 5-step reaction, which is something that I probably won't expect on the exam tomorrow. But we're sort of going in that direction for the final exam. Okay. All right. So this is just an example that kind of brings everything together. From multiple pieces of the course. I think by now you know that I like to do that. And so thinking about this retrosynthetically, which bonds are easy to form is the strategy here, right? It's going to take a lot of practice, and we certainly will do a little bit more on Tuesday even. But I think by the final you'll have plenty of practice to answer the questions that I'll ask. But for tomorrow, remember 1 or 2 steps involving enolate chemistry.
For question 5 on problem set 9, can you go over that third reaction?
Yeah, I think that one was maybe a holdover from the previous section of the course, right? So this is enamine formation. Right? That's all this is. So remember, you can have a secondary amine attack a carbonyl. That's going to give you tetrahedral intermediate, like such, right? That is going to, let's say, grab a proton. And then we said that the nitrogen lone pairs are one way that you can get an aminium ion with loss of hydroxide as a leaving group. Those lone pairs are actually fairly reactive enough so that OH minus is a leaving group. And then the OH minus actually is the thing that does a deprotonation to give you the enamine. Right? So the enamine the aminium ion does a deprotonation very similarly to the way an enolate actually forms. Think about this, right, molecule as just a masked enolate. Okay, if you look at the starting material structure, that aldehyde has alpha protons that are acidic. Well, this one does too. The aminium ion does too. All right, so this is why an example of why I put this in here because it resembles enolate deprotonation or aminium ion deprotonation to give you not an enolate, but in this case an enamine. Right, so again, trying to relate it to something you've seen previously. Okay.
Thank you.
From the same page, can we go over like the first reaction, like how we do that one?
Yeah, that's a Robinson annulation, right? So I drew this molecule in its enol tautomer, right? But overall, that reaction will occur to give you this species. Okay. You'll be able to see that molecule right there is actually this one. This one here is this one. Now, how do I know that that's the case? This one is in equilibrium with the diketone, remember. Okay. This 1,3-dicarbonyl is probably, well, I'll put it this way. These lone pairs here are in complete conjugation, right? So don't you want to have things in conjugation because that makes the molecule overall more stable? And so this molecule is in the enol form, but that doesn't mean it certainly can't make the keto form. But if we were to treat this molecule with sodium hydroxide, we're still going to get deprotonation of that proton right there. Oh, sorry, I guess it was catalytic phosphoric acid. Sorry. Let me go back. Getting ahead of myself. Okay, so this reaction is not under basic conditions, it's under acidic conditions, but we can do the same kind of chemistry. Okay, what's the first step in a Robinson annulation?
Michael addition.
Michael addition. And so why don't we take this starting material molecule, this enol form, and do a Michael addition. How do we do that? We're going to take these lone pairs. We're going to take the double bond, right? And we're going to attack that beta position. Electrons are going to move in this direction. Okay, so I'm going to sort of move this around a little bit. I'm going to say, okay, that's this carbon here. Okay. I still have the carbonyl over on this side. I've got now a Michael addition product in which I've got O minus as such, right? Okay, we're going to grab that proton to form a neutral species. That molecule is in equilibrium with its keto form. So we can draw it like this, right? This is just a tautomerization. Why don't we then form the enol on the other side? Because what's the second step in a Robinson annulation?
The
an aldol reaction, right? And so what do we need to do for an aldol reaction is to take this carbon atom right here and do a condensation onto that carbon atom right there. But in order to do that, we need to get it into a form in which it's reactive. So we're not going to form an enolate this time, but what we're going to form is actually an enol, which has the same kind of reactivity. So why don't we protonate this? And when we protonate that, this proton becomes more acidic. So now water in our phosphoric acid can come along, do a deprotonation to give us an enol. Like this. That enol can then do the aldol reaction. Okay. Okay, we've got carbonyl here. Right, so this carbon atom right here is that carbon atom right there. Okay, still got a proton source hanging off of that formerly enol functional group. We can do a series of proton transfers. So those oxygen lone pairs are going to grab that one there. Okay, and we get that kind of species. We're under acidic conditions. And so what's going to happen? is we're going to protonate again the carbonyl. We need to get rid of that OH. So what we can do is protonate the carbonyl, have water come in and form the enol by deprotonating again. Right, so this is under acidic conditions. So everything is now deprotonation, excuse me, everything is now protonated instead of deprotonated. So everything occurs from the enol form, not the enolate. But you can see kind of the same kind of pattern here for the Robinson annulation. What we're going to do now is an E1CB. Almost home. Okay, and then OH minus, that was the leaving group before, is going to grab that proton to give you your product molecule. All right, so this is an acid catalyzed Robinson annulation. Okay.
Thank you.
Sure.
Can you go over number 3 on the practice exam? Part A.
Remind me what year that was? Is that 2017?
2017.
And I'm sorry, number 3A.
Mm-hmm.
Okay. Yeah. So what is the transformation here? The transformation is squiggly line. All I have is a carboxylic acid converting into an amide. The particular amide that I'm using is hydroxylamine. Okay. And we're using this carbodiamide called EDCI. Right, so EDCI looks like this. It looks a little bit different than the carbodiamide that I gave you, I think, in class, DCC, but it acts the same way. Okay, so don't lose the forest for the trees here. The only thing that is involved in this reaction is that carboxylic acid functional group. Okay, so the first step in this amide formation is the deprotonation. So the lone pairs on nitrogen are going to grab this proton right there and to form a carboxylate. All right, so we've got this carboxylate, O minus, plus the carbodiamide is like this. And I'm just going to label this R and R so that we keep things a little bit simpler. Okay. So far, so good. Okay. This carbodiamide is rather electrophilic at the carbon atom, right? It has a big delta plus charge. And so this oxygen lone pair on the carboxylate can go in and attack, and it moves electrons up onto the nitrogen to relieve that positive charge. Okay, so we've got a new oxygen carbon bond now. Okay, so we've got R group there, and this is now C and R. Okay, makes sense? Now this this carbon atom right here is actually pretty electrophilic now, right? It's got large delta plus. And in the reaction of an amide coupling reaction, what we can do is we can take the nitrogen lone pairs on our amine and attack that carbonyl carbon. It's almost like this, this whole thing here is going to be our superleaving group. Right? Eventually that's going to turn into our urea. And so why don't we take the nitrogen lone pairs on that hydroxylamine and attack that, that carbon? What would we generate? All right, messed up. Okay, and then our hydroxylamine comes in here, NH2OH plus. Okay, let's get rid of one of those charges. So let's grab a proton there off of the amine. It gives us OH, NH, OH, and then our superleaving group system. Okay, and now at this stage, what can happen is you can collapse that tetrahedral intermediate with loss of the leaving group. And this time, the leaving group is going to be your urea. All right, so we've got now positive charge, NH-OH, right? And our urea is this functional group. And what we can do is simply move these electrons down, take the carbon nitrogen double bond and do a deprotonation to give us the product molecule, plus as our byproduct, a very stable urea. Okay, this is a very stable molecule. Think about it, you've got two lone pairs on each of these nitrogens that's pushing electron density towards the carbonyl. Okay. And so that carbonyl itself is not very reactive. Okay, so electrons are quite delocalized in this system. And so it's a very stable molecule. And so you end up with the amide as your product. So this is just an example of an amide coupling reaction. I think we use DCC as our coupling agent. This one here is EDCI, just a different version of the same kind of reactivity.
On that same exam, could you do the ranking problem, which I believe is 2B?
Yeah, okay, so we've got this one, we've got this 1,3-dicarbonyl, we've got this one here, and then we've got this one. Okay. All right, so we need to take a look at the enol. What did I ask for? Did I say enolate formation or did I say acidity or ketoenol? Ketoenol. Okay, so one is the most enol. Okay. So we want the most enol here is number 1. All right, so why don't we take a look at what particular proton in each of these cases is going to become enolizable. And so how about that for that first one? How's the enol going to form?
Remove a proton from one of the alpha positions.
Okay, so we're just going to form an enol like this. Okay, how about that second one? Where's the enol going to form? You got multiple positions that have alpha protons, right? You got an alpha proton there, 2 alpha protons there, 3 alpha protons there. What's the most stable enol form for that molecule?
The one in the middle.
One in the middle. So our enol is probably going to be something that looks like this. Okay. How about the third one? Now we got 2 methyl groups in the middle. So where are our alpha protons? They're only at the ends. So let's just pick one. Our enol is going to look like that. And how about the last one?
The alpha position to the right of the carbonyl.
Okay, so we're going to form this enol right here. Okay, so let's try to evaluate these. What's a enol form, or can you find a couple of enol forms that are really good or really poor, or they might be similar to one another?
Would the aromatic ring have the most enol?
Okay, so we're talking about this one right here. Okay, Lauren suggested that, it was Lauren, right? Okay, yeah, Lauren suggested that this one is going to be the most enol. What do we think? Why would it be better to have enol in this case? Why is it really really heavily favored towards the bottom? Right, normally enols aren't favored, right? But why would this one be favored? Go ahead, Lauren.
It's like a 4n plus 2.
Right, you've got an aromatic ring here, 4n plus 2. This is not aromatic. It's not aromatic because you don't have full conjugation. And so the driving force here for enolization gives you aromaticity. Right, so this one's aromatic. And we of course know that aromaticity is really important, much more important than resonance is even. Okay, so this one is going to be number 1, most enol. Now, where else do we have enolizable protons that are actually pretty stable?
The second molecule,
What about the second molecule?
there's resonance.
There's conjugation. If you were to take a look at this enol form, right, you've got electrons that could be delocalized throughout this system. There is resonance if we take a look at the deprotonation of this molecule. So let's say we took, OH minus, right? We could deprotonate this molecule, and what would we get? That we would get a system that has a negative charge here that could delocalize in both directions. Okay, so this negative charge, right, is delocalized into 2 carbonyls instead of only 1 carbonyl. If you compare that resonance form to the other 2 molecules, you can only do resonance upon deprotonation in a single direction because there's only 1 carbonyl. Right, so again, this is a logic problem. If you can resonance delocalize a negative charge, what it tells you is that for sigma donation of the enolizable proton, that enolizable proton can also sigma donate into 2 different carbonyls. So it's much more likely to become an enol if it has 2 different directions that it could go, right? And so the more acidic the proton is, the more stable this conjugate base is going to be, but also the more enol you're actually going to form in the first place. So this one is number 2. Okay, so now we have to compare this first one and the third one, both of which give you enols that are only delocalization into a single carbonyl. So how can we distinguish these 2? What's the difference between these 2? For that second one, just ignore this part of the molecule. It's not involved, right? So how do these molecules differ? They're very similar in the sense that that proton is only delocalizing, I'll draw it in here as well. That proton is only delocalizing into a signaled carbonyl. So it can't possibly just be sigma donation. It's got to be something else going on here. How might you distinguish between these 2?
Are there more
First-
protons to move with the ring?
Well, in the case of the first one, there's 2 protons. In the case of the second one, there are 3 protons. That's true. That really doesn't have any effect on the keto-enol tautomerization.
The first one is more highly substituted, so would it be more stable?
Okay, so if we're taking a look at this one, that enol has 2 carbon-based groups hanging off of it. Whereas for this one, the third one, it only has 1 carbon-based group hanging off of it. All right, so this is a di-substituted system, whereas this one is a mono-substituted system. And you know from last semester that di-substituted alkenes are much more stable than mono-substituted alkenes. If di-substituted alkenes are more stable than mono-substituted alkenes, it is also true then that di-substituted alkenes that are in their enol form are more stable than mono-substituted alkenes in the enol form. So if they're more stable, they're going to form more enol, and so that means this is 3 and that's 4. Okay, when you're trying to answer these questions, remember, this is just a logic problem. Okay, figuring out where the patterns are, right? Trying to determine what's similar, what's different between all the various groups, and then reasoning through if this, then that. Okay. Okay. Okay, somebody asked a question to me directly about problem set 9, number 3. Whether that a question like this would appear on the exam tomorrow. Again, remember, what I will say is that you should be able to do retrosyntheses that are 1 or 2 steps. Okay, we will leave questions that have multi-step syntheses for the final exam. This question was really one that tried to, ask you to think about what kinds of bonds are you trying to form here. The other thing that this question is asking is, do you know something about stereoselectivity when we add these chiral auxiliaries onto a molecule? Okay. All right, so we're trying to build up your repertoire of reactions that can occur via retrosynthesis. Okay, how do you form certain chemical bonds?
Dr. Mulcahy,
Yes, go ahead.
for one of the retrosynthesis problems that you did in office hours, I have it written down. I don't know if you can really see it. It had like that 3-ring system with
Yeah,
the
hold on.
benzene.
Let me just draw it. Hold on.
Okay. Oh, sorry.
I think I know. Something like this. Was it chloro? Like that? Is that it?
Yeah.
Yeah, go ahead.
So I think that when you did it in office hours, the first step that you did was you split the bond, like between the. I think that let me just remember. I think you split the bond between the the benzene group and like the other 2 rings.
This
Could
one?
Oh, I'm sorry, the other one. So like with the alcohol.
This
on
one.
that. Yeah. Could
Yeah.
you do the other way, like with the
Yeah. Again, I think remember that there are multiple ways of doing this, and sometimes if you have to do 2 different enolate forming reactions that react with an electrophile, a lot of times you can do it in either order. So if you wanted to do the aldol reaction first, followed by the aldol condensation or Claisen-Schmidt reaction, that's fine. That would be full credit. If you wanted to do the Claisen-Schmidt reaction first, followed by the aldol, that's fine too. And so there are multiple ways of trying to do some of these kinds of transformations.
Okay. And then, so if you did do it the way that I mentioned, would you avoid doing a Muciano condensation, or would you have to do that regardless?
Okay, so remind me again, which reaction did you want to do first?
If you split the like alkene on the left side.
Okay, so let's just do that. Okay, what we're gonna do is split up this reaction here. Okay, So in order to do that, what we would have to do is first form our alcohol. Okay, and then we would do the E1CB from there. And you can see that there's going to be a problem. And the problem is if you take sodium hydroxide and you do the E1CB, you've got two different enolizable protons here that could form alkenes for either of those two aromatic systems. Right? So I think this is why that other method is better. You could do it, but what you would have to do is you would have to protect the alcohol. One way of protecting that alcohol is to protect it as an acetal, but that's probably a little bit steppy and not something I would really want you to do. I would want you to do this in a minimum number of steps, and so that's why the other way is preferred. But if you came up with a synthesis in which you protected that alcohol, then that would be perfectly correct. Okay.
Thank you.
Sure. Again, I want to reiterate these retrosyntheses problems for the exam. It's going to be one or two steps, right? So don't try to focus so much on the retrosynthesis that you ignore some of the other parts of this section of the course, right? There's some theoretical parts of the course that I want you to know, right? It's going to be as evenly distributed as possible, even though in workshop over the last couple of days, we've been focusing on retrosynthesis, and that's mainly because of the final exam, okay? And don't forget nucleophilic acyl substitution, right? That's going to be probably 50% of the exam, right? Additions to carbonyls, substitutions of carbonyls. Reactivity series, etc.
For one of the molecules that you gave us, it was potassium hexamethyl, and then what was the end of it? Sorry, I just missed the end in class.
Yeah, KHMDS. Sorry, I may have been a little bit too quick here. This is potassium hexamethyl disilazide. Okay, KHMDS is what we normally abbreviate it as. Of course, you could have LHMDS, which is the lithium version, NHMDS, which is not really used that often. But KHMDS and LHMDS are molecules that have similarity in a way to LDA, right? Just a little bit bulkier than LDA, right? So you've got silicon with 3 methyl groups, 2 of those silicons with 3 methyl groups each, right? Potassium hexamethyl disilazide.
Thank you.
Sure.
Is it test at 6 or at 7?
Test is at 6. Okay.
Set.
At 6
Okay.
o'clock.
Thank you.
Sure. It's still a lot of time to study. I think everybody's going to do just fine. There's a lot of stuff here. This is as challenging as it gets, but I've been pretty happy over the last couple weeks. So with where everybody is, so I think we'll do just fine. So get a good night's sleep. Don't forget to call your mom if it's not too late. Right, it's Mother's Day, and we'll pick back up here tomorrow. So again, no office hour tomorrow, but if you need some extra help, I can do a one-on-one. I've got a little bit of time. I'm giving another exam in the morning, one of my other classes, but I know this is challenging stuff. Any other questions? Okay, if everybody will indulge me a little bit, I want to try to save as much of our time on Tuesday as we can to problems. So I'm posting into the chat right now the link to the evaluations. So if you have some time, what I'm going to do is I'm just going to mute myself and turn my video off and walk away. And if you could fill out the evaluation form for the course, that would be really helpful as a guide to what to do better next time. So you can click on that link there, and then when you're finished, just sign off, and I'll come back in 15 minutes or so and shut down the Zoom call. Okay. All right. Any questions before we? Any final things before before I leave the room? Okay, folks. We will pick back up here tomorrow. All right. Zoom call. You can enter the Zoom at probably like 5:45 or so. I will be emailing the exam to you. Okay, email. All right. All right. I think a couple of you are taking exam at a different time. Again, I will email you the exam at that time. Okay. All right. Thanks.